Now, vectors and scalars are really important for you. All quantities in physics are either a vector or a scalar. It's not quite true, but I'll ignore the complexity of the other types of quantities which you don't meet on this course. Okay, a scalar has just got a size. And we don't like the word size because that's just too obvious. Or a magnitude. No one knows what the word magnitude means, so that makes it seem like we're special. And I should point out we're all special in our own way. Okay, well, a vector has a magnitude plus a direction. Now, it does make vectors useful. The direction information is very important. As a quick idea, if I said to you that a car travels at 50 miles per hour, that's its speed for 1 hour, that's the time, and I said if it starts at a certain point, speed is distance over time, then what is the distance travelled? Then the distance travelled is 50 miles. If it does 50 miles an hour for 1 hour, it's travelled 50 miles. If I then said, where is it compared to the starting point? The answer is you don't know. What you do know is it's somewhere within 50 miles of the starting point, but it could be 0 because it could have done a big circle with a circumference of basically 50 miles or some erratic path that ended up at the same point 1 hour later. All you know it is within 50 miles of you. If I said to you it travelled 50 miles an hour north and then it turned around quickly and travelled 50 miles an hour south, and it was half an hour for each of those parts of the journey, then you'd know I'm back at the beginning again, because it's like 30 minutes worth, 25 miles going north, and then it turns around and it does the 25 miles to come back. The crucial information is the direction. There are some quantities like velocity, like force, where if you want to be able to say everything, work everything out, we need the direction information. Now this does make them slightly more complicated when we add them up. So all I want to do is I'd like to go through how you work out their components, and then I'd like to give you the hardest question that they can give you in an exam, which does come up, and we'll look at how it works. So let's suppose that's the y-axis and that's the x-axis, and I'm going to draw a vector like that. I'm going to call it V for vector. It doesn't mean velocity, it means it's a vector. Normally we draw the direction to the x-axis. You don't have to, but that's normally what we do. And we use the Greek symbol theta. And what you're supposed to realize is that if I look at the components of the vector, if I want, for example, the x component, what that means is, if I zoom in here, if you look at the head, this is called the tail, this is called the head. If you look at the head of the vector, you have to draw a line from the head of the vector to the x-axis, and it has to hit the x-axis perpendicular. So in other words, if I drew that line, that is not hitting the x-axis at a perpendicular. So what I would do, of course, is draw that one, because that's a perpendicular. That defines Vx. And the one I've drawn here would be that one. And that's Vy. So essentially what I've done is I've turned this into a right angle triangle. If I was to say, do something slightly crazy, like imagine that this is a projectile and the ground wasn't flat, but it was on an angle phi. Then, and I said, what is the component of the vector v in the direction phi? Then again, what you're doing is you're saying, draw a straight line from the head to the point at which it touches that line, and it has to be at a right angle. So I'm talking about that length there. That's what we mean by a component of a vector. It's a slightly unusual way of thinking about it, but that's what it means. And so you're always looking basically to turn a vector into like a triangle of vectors, and the triangle is made up of its components. And it means that I can write v squared is vx squared plus vy squared. It also means I can write sine theta is Vy over V, cos theta is Vx over V, and tan theta is Vy over Vx. Now some people are absolutely fine with that, and some people sort of randomly seem to forget. They know it's sine and cos, but they can't remember which one it is. And so I've got a way of telling you how to do this faultlessly every time, and it's really simple as long as you understand the argument I'm using. Imagine a clock for a moment with its hands. That's the small hand, that's the large hand, that's the hour hand, and this is the minutes hand. So that would be 3 o'clock. And imagine just the moving round of the hand. Imagine that this hand here, the minute hand, moved around by that amount. And you, as long as you can imagine that idea and say, well, what is that angle? Then you can do this idea I'm about to tell you. The component of any vector in any direction is given by V, and I'll put question mark because that means like Vx or Vy, or maybe V phi, as we just saw. V question mark, the question mark is the direction we're interested in, the component, is V, the vector, multiplied by the cosine, always the cosine, of the angle you turn the vector through so it points in the direction you want. So imagine, for example, that I've got my vector there, and let's suppose that was 35 degrees, and that's V, and I said I want Vx. Well, imagine that is the hand on the clock, and I'm asking for the x component, this bit. Well, what you do is you see the fact that I've got to turn that vector through 35 degrees. The hand has got to move through 35 degrees in order to point in the x direction. So Vx will equal V, whatever V is, cosine 35. And that would be Vx. Now what about Vy? Vy is going to be V, and it's going to be, if I wanted to point it in the y direction, I'd have to take this vector, which is looking very fat now, and I'd have to move it around to there. Well, if that's 35, then this is 55. So it's V cos 55. Now, if you look at this lot over here on the left-hand side, you'll see that Vx, by rearrangement, does equal V cos theta. So that one's correct. But I've written Vy in a slightly different way. Vy is V cos 55, whereas over here, Vy is V sine theta. So what I'm telling you is that's the same as V sine 35, which is the way you would normally write it, V sine theta. And if you don't believe me that basically cos 55 is the same as sine 35, then just get your calculator and type sine 35 divided by cos 55, and you'll see that the answer is 1. And this is quite a useful idea if you're the kind of person that often doesn't know how to work out the components of the vectors. It's a really quick, easy way of always getting it right. So it's always based on cos. So if I just had theta, then Vx would be V cos theta, and Vy would be V cos 90 minus theta, because that's the other part, because that's a right angle, of course. And let me show you, and I'm going through this quite quickly, so let's do an example. And it's basically an object on an incline. So let me draw an incline. And you place an object on it. And like a box. And you say, okay, the box is stationary on the incline. The incline has got an angle theta. If you're drawing this, don't go for 45 degrees. We've got to think about 45 degrees. That's still not 45 degrees. We kind of love 45 degrees, but it's not good for you. Okay, and there are actually 3 forces acting on this box. There is a weight. There is a friction force up, the slope. The weight is directly downwards in the direction of the gravitational field strength towards the center of the Earth. The friction force, people think incorrectly that a frictional force is a force that opposes motion. That's not true. A frictional force is a force that opposes motion or the tendency to move. If I place an object on an incline and the incline's not too big, it will just sit there. Imagine that I actually change that situation for something like this. There's the x-axis, as it were, the ground or the lab bench or whatever. And imagine that my incline was actually, it had holes in it. And it was actually an incline that you could pump air into. So it was like an air track with like air coming out of the holes. So when I place the object on there, it actually isn't touching the track because it's floating on a layer of air. Well, what would happen then is it would glide, accelerate actually, down towards the bottom because of the lack of friction. The friction here is holding it in place against its tendency to move down the slope. Okay, so that's the friction force. There's another one, which is the reaction force, and that's at right angles to the surface. A reaction force is the force from a solid object when you push against it, and it's the force it pushes back. If I place something like a piece of wood in water, it floats. There's a gravitational force downwards. We do not call the opposite force that makes it float a reaction force. We call it a buoyancy force or an upthrust. Upthrust, students seem to like the word upthrust. It's like any force that's upwards is an upthrust, and that's not true. An upthrust is the upward force on an object because it's surrounded by a fluid. So anyway, let's get back to this. Now this, what we'd like to do is look at the relationship between those three. Now what we do, we draw what's called a force diagram. It's also got another name. It's also called a free body diagram. And the free body diagram, they basically have directions indicated. So I'm going to do X and Y like that. They also have other important directions if they are important. In this case, there's the theta. Now this is why 45 degrees is not good. You'll see why in a second. Make your angle quite small. So you can imagine that that orange X and Y, it was the X and Y axis, and it's just been rotated by a small bit. And so you can see that that's theta. Theta is the small one. This is why 45 degrees is not such a good angle to show. Because if you did 45 degrees, all of your angles look the same. Right, there's the one, and there's the other, and every single angle is the same as every other angle, and it's just more likely to allow you to make a mistake. That's all. Now let's put the forces on. So we've got a weight. I'll draw a dot for the object. The object is the box, but now it's just a dot. We've got weight downwards. We've got FF up the slope, and we've got the reaction force at right angles to the slope, so that's going to be like that. Now, okay, when I have that, I can look at this diagram, and I can basically say, let's take components of vectors. Horizontally, so in other words, the direction that I'm interested in is this direction, that's the horizontal axis. Horizontally, I can see that FF has a component in that direction, which would be like that, so to the right. And I know how to do it now because it's just FF cos theta, cosine of the angle you turn it through. FF cos theta equals, because R has got a component, but that's to the left, so that's in opposition. And so that's going to be R. Now, so that I don't mess up now, it's going to be R cos 90 minus theta. It's that angle. Imagine again, it's the hand on a clock. I've got to turn R through 90 minus theta to get it around to the horizontal direction. So it's R cos 90 minus theta. That's the same as sine theta. So I could just get rid of that and write sine theta. I can ignore W because W is at right angles to the direction I'm interested in, so there is no component. So that's horizontally, that's it. Right, vertically, R has got a component up like that, and FF has got a component up like that, and W is the whole vector downwards. It's going to be, I don't have to turn W through any angle to get it vertical. In other words, the angle is 0. And so that would be like W cos 0. And the cosine of 0, of course, is the finger. A 1, I mean. Okay, so vertically, we can say it's going to be upwards. It's going to be R cos theta, because that's the angle I would have to turn it through. There. Plus, there's another one. It's FF. And I know now it's cos 90 minus theta. And that's the same as sine theta. Equals, and then it's just W cos naught, which is just W. And that's it. Now those two equations then are considered to basically contain all of the information for this particular situation. However, there are two other directions we could consider that are far more useful. There is parallel to the incline. Now, parallel to the incline basically means that direction there. So in other words, up and down. My next direction is going to be perpendicular to the incline, which is that direction there. Okay, now, when it's parallel to the incline, I can ignore R because it's at right angles. So basically, this allows me to write up is FF, directly up, it's cosine 0. And then equals, and this is where this idea pays off, I think, because W, if you say to yourself, what angle have I got to turn W through to get it along this line? It's that, which is 90 minus theta. So in other words, sine theta. So it's going to be W sine theta. And then if I do perpendicular to the incline, R is directly upwards, and it's R without, it's cos 0, so 1, R. I can ignore FF because it's at right angles, and that's going to equal W, and I'm interested in this direction, and I got to turn W through theta, so it's W cos theta, and that's it. So these two equations are supposed to be simpler, and they are, than those two equations, but they contain all the same information. It means that if I look at these two, I can see that there is a remarkable similarity between them. If I do W sine theta divided by W cos theta, that's the same as, it's just tan theta. So I've got tan theta is FF over R for limiting friction only. So this bit here is for limiting friction. So in other words, just when it's about to slip. The frictional force is given by the so-called friction coefficient, mu, the reaction force. And of course there's an R on the bottom, so that gives me mu is equal to tan theta. And this is how we work out the frictional coefficient, by measuring that angle and then tanning it. Right, okay, and that's it. That's probably the hardest question they can ask you about multiplying vectors. And if you can cope with all that lot, then you're in a good place.